In chapter 6, we're going to learn mechanical properties of metals. The first concept we're going to learn is called stress-strain diagram. This is one of the most important diagram to show you the stress-strain behavior of a given material. Let's first look at an example of such diagram. And here is a drawing of a stress-strain diagram. On the y direction, we have stress. We use sigma to represent stress. And on the x direction, we have strain. We use epsilon to represent strain. And let's first look at what is the stress, what is the strain. Okay, start with stress. Change color here. Okay, what is stress? We define stress sigma equals F divided by the area. Okay, F is a force, A is the area that the force is applied on. And by looking at the definition of the equation, we know and stress should have units like Newton per meter square, or you can write this as Pascal, kilopascal, or gigapascal. You can also use PSI as the unit for stress. So why we need to use stress instead of using force? You took statics and dynamics. In those courses, you learned how to deal with stress, how to find force. Force could cause an acceleration and cause the movement. But why we need to use stress in this course instead of force? Like, let me give you an example. For example, let's use a 20-pound force. And if I just throw you this number, 20 pounds, and is this a large or small? Some of you may say it's large force, some of you may say it's a small force, and however, it is hard to say. It depends on where is this 20 pounds force is applied on. If this 20 pounds of force is applied on a fairly large surface area, and the intensity of the force can be small and the effect is pretty slight. And if this 20-pound force is applied on a very tiny small area, and this gonna create a large stress, so the intensity of the force is high. So the stress can be think of as the intensity of the force. And this will help you to understand why we need to use stress in this chapter. Okay, another concept, one is stress, another concept is strain. And this is a fairly new concept. And what is strain? Strain epsilon is defined by change of the length divided by the original length. Here, what length we're talking about? We're talking about the specimen or any materials under load under a given stress. So, for example, if we have a bar has an original length of L0, and we can start to apply force on both ends of the bar, and we know after you apply certain force, it could cause deformation. The length of this bar gonna be increased if the load is large enough. Let's say Now the bar has a new length of L1. Of course, the change of length here is going to be delta L. And the original length is L0, which is, and now you can either replace this delta L with L1 minus L0 divided by L0. Okay. So similar with stress, this strain gives you an idea of how intense is the deformation. And similar example, if I just throw you a number, let's say, just tell you delta L, the change of length of a material under certain stress is, let's say it's 2 centimeters. Okay, now I want to ask you, is this 2 centimeter strain change of length a fairly large deformation or small deformation? The answer is depends. If you have a very long bar with the original length, let's say 20 meters, 2 meters, or 20 meters, let's make it more, 20 meters. And after you apply a stress to this material, the change of length is only 2 centimeters, which is 0.02 meters. And this change of length, when you compare this change of length to its original length, 20 meters, and the deformation, it's fairly small, right? And another extreme example, what if our original length of this bar, L0, it's only 10 centimeters. Now if you compare the change of length 2 centimeters with the original length 10 centimeters, the change of length is about 20% of its original length. Then under this condition, the deformation is significant. That's why only looking at the change of length delta L would not tell us enough information about deformation of a material under certain stress. That's why we need to use this concept strain to describe the intensity of deformation.